Chemical properties of alcohols. Chemical properties of alcohols. Chemical properties of alcohols. Based on the cleavage of OH bond and CO bonds, the chemical reactions or the chemical properties of alcohols may be divided into two groups. So, based on the cleavage of OH bond and CO bond. Based on the cleavage of OH bond and CO bond, the chemical properties or chemical reactions of alcohols, chemical reactions of alcohols may be divided into two. First one, reactions involving cleavage of OH bond. Reactions involving cleavage of OH bond. Reactions involving cleavage of OH bond. Second one, reactions involving cleavage of CO bond. Reactions involving cleavage of CO bond. Carbon oxygen bond. Similarly, first one, reactions involving cleavage of oxygen hydrogen bond. Second one, reactions involving cleavage of carbon oxygen bond. Carbon oxygen bond. Reactions involving OH bond and reactions involving carbon oxygen bond. So the first one, here we consider this first one, reactions involving cleavage of OH bond. 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 First one, acidity of alcohol. First one, acidity of alcohol. So these alcohols are feeble acidity. Alcohols have feeble acidity. This acidity is illustrated by the fact that they react with metals such as sodium, magnesium, potassium, aluminum, or such metals to yield metal alkoxides. So these alcohols are feeble in acidic nature. This is illustrated by the reaction of alcohols or OH plus metals such as sodium, aluminum, or potassium, or some other metals to yield metal alkoxide. Here this alcohol is reactive to sodium, we get sodium alkoxide and hydrogen. So this acidic character of alcohols is due to the polar nature of OH bond. Polar nature of OH bond. But they are only very weak acids, because the electron releasing alkyl groups increases electron density on the oxygen by plus I effect. So here this acid strength of alcohols is very weak. This weak acidity due to the presence of this alkyl group. So presence of this electron releasing alkyl groups. The electron releasing alkyl groups increases electron density on oxygen. Electron density on oxygen by plus I effect. Plus I effect. Plus I effect. So due to this plus I effect of this alkyl group, these alcohols behaves as weak acids. Weak acids. Now let us consider the order of acidity of alcohols. Order of acidity of alcohols. Order of acidity. That means order of acidity of primary, secondary, and tertiary alcohols. Order of primary, secondary, tertiary alcohols. Now let us take an example. CH3 CH2OH, CH3 CH2OH, then CH3 CH3OH, here CH3 CH3OH. So first one is, this is ethanol. It is a primary alcohol. Then this is propan 2-ol. Propan 2-ol. It is secondary alcohol. This is this alcohol is 2-methyl propan 2-ol. 2-methyl propan 2-ol. This is tertiary alcohol. So here in this tertiary alcohol, three alkyl groups are present. Here 3 alkyl groups are present, but in secondary alcohol 2 alkyl groups are present. In primary alcohol 1 alkyl group is present. So greater the number of alkyl groups attached to this carbon, greater number of alkyl groups, here methyl groups, greater number of alkyl groups attached to this carbon carrying this OH bond, the polarity of OH bond decreases. Polarity of OH bond decreases due to the plus I effect of this alkyl group. Due to the plus I effect of this alkyl group. Hence, the acid strength of alcohols decreases in the order primary, secondary, and tertiary. Primary, secondary, and tertiary. So primary alcohols are more acidic than that of secondary and tertiary. Here this ethanol is more acidic than propan 2-ol. Propan 2-ol, and this propan 2-ol is more acidic than that of this one, 2-methyl propan 2-ol. So the acidic strength of alcohols decreases in the order primary alcohol is primary alcohol is more acidic than that of secondary alcohol. Secondary alcohol is more acidic than that of tertiary alcohol. So among primary, secondary, and tertiary alcohols, primary alcohols are more acidic. Primary alcohols are more acidic. These alcohols are, however, weaker acids than water. This can be understood by the reaction of water with an alkoxide, or O minus plus HOH is ROH plus OH minus. Here this is base, acid, conjugate acid, conjugate base, conjugate base. So this reaction shows that the water is a good proton donor, that is strong acid than alcohol. Also in this reaction the alkoxide ion is a good proton acceptor than that of hydroxide ion, which suggests that these alkoxides are stronger bases, or the alcohols act as Bronsted bases as well. It is due to the presence of unshared electron pairs on oxygen, which unshared pair of electrons on oxygen, which makes them proton acceptors. So this is the acidic character. These are all about this acidic character of alcohols. Second one, formation of esters. Or simply esterification. Esterification. So here these alcohols react with carboxylic acids, acid anhydrides and acid chlorides to form esters. So alcohols react with carboxylic acids, acid anhydrides and acid chlorides or acid halides to form esters. These reactions are generally known as esterification of alcohols. So here first one, reaction with carboxylic acid. Reaction with carboxylic acid. Reaction with carboxylic acid. Reaction with carboxylic acid. So these alcohols react with carboxylic acid in presence of an acid will yield esters. So here this alcohols react with a carboxylic acid in presence of an acid will result in ester. Will result in ester. So the reaction is usually carried out in the presence of small amount of concentrated sulfuric acid. The presence of concentrated sulfuric acid ensures the removal of water formed and thereby shifts the equilibrium of this reaction towards right. Now let us take an example. CH3 C double bond OH plus C2H5OH. We get CH3 C double bond O C2H5 plus H2O. Now next, Fischer esterification. Fischer esterification. Or Fischer Spear esterification. Fischer spare, SPE, spare esterification. So here in this method, or this Fischer esterification method, consists of heating a mixture of 1:1 mixture of alcohols and carboxylic acid in the presence of concentrated sulfuric acid or dry HCl. In the presence of concentrated sulfuric acid or dry HCl. In the presence of concentrated sulfuric acid or dry HCl. So R C double bond O OH plus R dash OH presence of dry HCl, or it is used, it may be used as concentrated sulfuric acid. So concentrated sulfuric acid is also used for this reaction. What we get, R C double bond O R dash plus H2O plus H plus. So this is Fischer esterification reaction. Fischer esterification reaction. Now let us check the mechanism. Here first, R C double bond O OH plus H plus, that is H plus from HCl or concentrated H2. So for H plus we get R C double bond OH plus OH. Here this pi electron shifted to here, then that is I'm going to do R C plus OH OH, then plus R OH alcohol R dash OH, and then it will attack here, and then we get R C OH 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 R dash plus. Next step, here this this shared pair of electrons transferred to here, and this OH minus removed, and this shared pair of electrons transferred to here. So total one water molecule and one proton is also removed. What we get? We get R C double bond O R dash plus H2O plus H plus, H2O plus plus H plus. So this is the mechanism of this Fischer esterification, or Fischer sphere esterification. We know that this OH bond is slightly polar. When more number of alkyl groups present here, that is this alcohol, it may be secondary or it may be tertiary or it may be primary, or when the number of alkyl groups increases or the alcohol changes to primary or tertiary, there is an increase in the plus I effect of alkyl group. That makes the cleavage of OH bond difficult, and the alcohol becomes less reactive towards esterification. That means when the alkyl group attached on the carbon which is bonded to OH is increases, that makes more plus I effect on that carbon. So that type of alcohols becomes less reactive towards esterification. That means for esterification is also primary alcohols are easily undergo esterification reaction, then secondary and then tertiary. So here also this reactivity towards esterification is in the order of first alcohols, methanol, then primary, then secondary and tertiary. Secondary and tertiary. So here this reactivity of alcohol towards esterification is in the order. First one, methanol is a primary alcohol, but it is a small one carbon atom is there, so it is more reactive towards this visceral esterification. The primary alcohol, first methanol, then second one primary, then third secondary, then last tertiary. So this esterification or the order of reactivity of alcohols towards esterification is methanol, then primary, then secondary and tertiary. Then here this steric hindrance also plays an important role in determining the rate of esterification. So the bulkier alcohol, or the bulkier alcohol means tertiary or secondary, the slower the rate of esterification. So the rate of esterification is high in the case of primary alcohol. So as primary alcohols can be easily undergo, primary alcohols can easily undergo this esterification reaction. Next, reaction with acid anhydride. Reaction with acid anhydride. Reaction with acid anhydride. Reaction with acid anhydride. That is, alcohols react with acid anhydride. Alcohols react with acid anhydrates in the presence of small amount of acid. The presence of small amount of acids. The presence of small amount of acids. Small amount of acids. We get an ester. We get an ester. So this is the reaction of an general acid anhydride with alcohol. Let us consider an example. Acetic anhydride. That is CH3, C double bond O, C double bond O, CH3. CH3 acetic anhydride plus ethanol or ethyl alcohol. What we get in presence of H plus? We get CH3, C double bond O, C2H5 plus CH3, COH. We get ethyl acetate. So this is the reaction of an acid anhydride with an alcohol. Now let us check the mechanism. Here first step, R, C double bond O, C double bond O, R plus H plus gives R, C double bond O, C double bond O, R, H plus. Next step, there R, OH, that is R dash OH. Take here, we shifted to here. What we get? We get R, C double bond O, C, O, H, O plus R, H, R. Next step, this R dash. Next step, this is shifted to here and this shifted to here. Then what we get? We get R dash O, it's R, I'm sorry, C double bond O, C double bond O, R plus, R COO minus. Then next step, COO, this H is attacked here, COH, R COH. Next step, this is shifted to here, and we get minus H plus, we get R O, R dash O, C double bond O, R dash O, C double bond, that is an ester. This is the mechanism of this reaction of an acid anhydride with alcohol. Acid anhydride with alcohol. Next, reaction with acid chlorides. Reaction with acid chlorides. Alcohols react with acid chlorides in the presence of a base like pyridine to form esters. So alcohols react with acid chlorides in presence of pyridine. We get an ester. So COCl is an acid chloride plus an alcohol in presence of pyridine. We get an ester. We get an COO R dash. We get an ester plus pyridinium ion. Cl is also the pyridinium chloride. So this is the reaction of an alcohol with acid chloride. Let us take an example. CH3 COCl, that is acetyl chloride plus ethyl alcohol, C2H5OH, in presence of pyridine. We get CH3 C double bond O C2H4 ethyl acetate plus this pyridinium chloride. Now let us check the mechanism of this reaction. So here R C double bond O Cl plus R dash OH. So just to take here, just transfer to here, and we get R C O minus Cl O H and R dash. Next step, this pyridinium ion, this pyridine takes this H plus from here and this is shifted to here. What we get? R. So this also shifted here. Then Cl minus, and what we get? R C double bond O R dash plus this Cl minus is attached to this pyridinium ion. What we get? Pyridinium chloride plus H C minus. So this is the mechanism of reaction of alcohols with acid chloride. Reaction of alcohol, reaction of alcohols. Reaction of alcohols with acid chloride. Next, reactions involving the cleavage of carbon-oxygen bond. Reactions involving the cleavage of carbon oxygen bond. Reactions involving the cleavage of carbon oxygen bond. Here first one, the reaction with hydrogen halides. Reaction with hydrogen halides. Reaction with hydrogen halides. Alcohols react with hydrogen halides to form corresponding alkyl halides. So alcohols, that is ROH, react with hydrogen halides, that is HX. We get corresponding alkyl halide. We get corresponding alkyl halide. Here this HX are HCl, HBr, HI, etc. Let us take an example. CH3, CH2OH plus HBr. We get CH3, CH2Br plus H2O. CH3, CH2Br plus H2O. In general, tertiary alcohols react rapidly with hydrogen halides. Secondary alcohols react somewhat slower, and primary alcohols even more slowly. The order of reactivity of hydrogen halide or hydrogen halides is HI greater than HCl. This HCl reacts only in the presence of a catalyst, anhydrous zinc chloride. There is no need of such catalyst for the reaction with hydrogen iodide or hydrogen bromide. So this is the reaction of alcohols with hydrogen halides. Next, reaction with phosphorus halides. Phosphorus halides. Reaction with phosphorus halides. Alcohols react with phosphorus halides like PCl5, PCl3 to yield corresponding alkyl halide. So this alcohol react with phosphorus halides like PCl5, we get corresponding alkyl halide plus POCl3 plus HCl. Example, CH3 CH2OH plus PCl5 gives CH3 CH2 Cl plus POCl3 plus HCl. Similarly, this alcohol 3ROH plus PCl3, we get alkyl halide plus H3PO3. So the reaction of alcohols with phosphorus halide yields alkyl halides. Then next, reaction with thionyl chloride. reaction with thionyl chloride. Thionyl chloride. SOCl2. SOCl2. Alcohols react with this thionyl chloride in presence of a base, that means pyridine. We get corresponding alkyl chloride. So these alcohols are converted to corresponding alkyl chlorides by heating with thionyl chloride heating with thionyl chloride in the presence of pyridine. So ROH plus SOCl2, thionyl chloride in presence of pyridine. We get alkyl chloride plus SO2 plus HCl. Example, CH3 CH2OH plus SOCl2 in presence of pyridine. We get CH3 CH2Cl plus SO2 plus HCl. So this is the reaction of alcohols with thionyl chloride. Reaction of alcohols with thionyl chloride, or reaction of alcohols with SOCl2. Next, dehydration. Dehydration. Alcohols undergo dehydration, that is removal of a water molecule, to form alkenes on treating with a protic acid. That is example sulfuric acid or phosphoric acid like H3PO4, or catalysts such as anhydrous zinc chloride or anhydrous alumina, etc. So these alcohols undergo dehydration. We get alkene. So alcohols undergo dehydration. What we get? We get an alkene. This dehydration are generally carried out by the help of a protic acid like H2SO4 or H3PO4. So this is an alcohol in presence of an protic acid, H plus heat. What we get? We get an alkene. So let us take some examples. First one, ethanol. CH3 CH2OH. Treat with H2SO4 around 443 Kelvin. We get CH2 double bond CH2 plus H2. Similarly, consider a secondary alcohol. CH3 CHOH CH3. This is secondary alcohols. 85% H3PO4. Similarly, 440 Kelvin, when we get CH3 CH double bond CH2 plus H2. Now consider a tertiary alcohol. CH3 CH3 OH. Take a milder condition, that means 20% H3PO4. Similarly, 358 Kelvin, we get CH3CH, sorry, CH3C. This is C, CH3C double bond, CH2, CH3 plus H2O. So when when alcohol undergo dehydration in presence of a protic acid, we get alkanes. Now let us consider the mechanism of this dehydration. This is an alcohol. It's an alcohol. Here first step is protonation. That is protonation step. The first step. H OH2 plus. Next step, formation of carbocation. This is the slowest step. Hence, the right deterministic step of the reaction is. Hence, this step is the following step is the right deterministic step. That is, this is the slowest step. That is formation of carbocation. That is the shared pair of electrons transferred to here. What we get? CH plus formation of carbocation plus H2O. Next, formation of alkene. Here, this shared pair of electrons transferred to here and removal of proton. That is, we get CH double bond CH plus H plus. So this is the mechanism of dehydration of alcohols. This is the mechanism of dehydration of alcohols. Now consider an example. So another example. CH3, CH2, CH2, CH2OH. Dehydration in presence of an acid. We get two types of alkene. That is, we get CH3, CH double bond CH3 plus CH3, CH2, CH double bond CH2. So here two types of alkenes are formed. This is the major product. This is minor. So actually what will happen here? So here the carbocation formed in the intermediate step. That is formed in the intermediate step should be a stable one. So here it must be remembered that as the mechanism involved carbocation intermediate, so the relative ease of dehydration of alcohols are exactly is in the order of stability of carbocation. So let us check here first. CH3, CH2, CH2OH plus H plus. We get CH3, CH2, 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 OH2 plus. So next step is transfer of this electron. What we get? CH3, CH2, CH2, CH2 plus H2O. So this is a primary carbocation. This is a primary carbocation. So this primary carbocation rearrange and to get rearrangement and to get a stable carbocation by 1,2 hydrogen shift. 1,2 hydrogen shift. That is here CH3, CH2, CHH, CH2 plus. Actually what happened here is this this hydride ion attached here. What we get? We get CH3, CH2, CH plus, CH3. So this is secondary carbocation. So this secondary carbocation is more stable than that of this primary cation. That's why this type of rearrangement occur, and then one of the hydrogen from eliminated from here. What we get? CH3 minus H plus. What we get? CH3, CH double bond CH, CH3. Here when hydrogen eliminated from this carbocation, what we get? H plus. CH3, CH2, CH double bond CH2. So from here one of the H plus is removed from here. So this dehydration of alcohols involves, or the mechanism of dehydration of alcohols involves a carbocation intermediate. So the relative ease of dehydration of alcohols is in the order of a stability carbocation. So this ease of dehydration of alcohols are in the order of tertiary alcohols can easily undergo dehydration, then secondary alcohols, then primary alcohols. So we can easily dehydrate tertiary alcohols, then followed by next one is secondary alcohol, then finally the ease of dehydration is very pure in the case of primary alcohol. Next, catalytic dehydration. Catalytic dehydration. Catalytic dehydration. Alcohols undergo this dehydration on heating with certain catalysts such as anhydrous zinc chloride or anhydrous Al2O3 alumina to yield corresponding alkene. So this catalytic dehydration means alcohols, example ethanol, undergo dehydration in presence of anhydrous alumina Al2O3 or anhydrous zinc chloride. We get corresponding alkene. So alcohols undergo dehydration on heating with catalysts such as anhydrous zinc chloride or alumina to yield alkenes. So these are all about the reactions involving the cleavage of carbon oxygen bond.